Okay, welcome to the 17th class meeting of EECE574, the graduate level probability and random processes. Last time I mistakenly said the class meeting number was 15, but it was actually 16. Anyway, homework 9 will be assigned, and chapter 5 is updated, so you'd better download it again. Messages from instructor. As a graduate student, you must have your own toolbox, but not only you collect tools, but also you must be very, very skillful, which means that you need a lot of practice with those tools. Got it? So try to fill up your toolbox and improve your skill. That is today's message. Let's overview what we have been doing. We reviewed during the first half part of this semester, the undergraduate probability and random variables and vectors part. And after the midterm, we moved to the graduate part, starting with sequence of random variables. Here, we use the Populist textbook, and it consists of first general concepts, and most of the materials are the same as what we covered using our undergraduate material, but I emphasize the order statistics and linear dependence and independence. You remember linear dependence among random variables as something like this. So if you have jointly distributed random variables x1 through xn, and if you linearly compute a weighted sum, and if its power or its non-central second moment equals 0, then what can you say? This is same as probability of event that your weighted sum of random variables equals 0 with probability 1, right? Which means that one of the random variables can be always written as the other random variables as a weighted sum. Of course, you can add, for example, some constant. In that case, you have an affine dependence or something like that. In section 7.2, I emphasize the sum of random number of random variables. So you have sum S that is random variable, which is summation of random number n of random variables. In that case, this behavior of the sum is much different from the deterministic sum, finite sum of pre-specified number of terms sum. And then I covered whitening a random vector. So here you have some random vector that has mean mu sub x and covariance matrix CXX. In that case, one of the way to whiten it is that you first subtract the mean, and then you multiply the square root of the covariance matrix, which is defined by using the eigen decomposition, not necessarily orthonormal, but you can use this definition of the square root of the covariance matrix. And then what do you have? You have some random vector y that has mean 0 and covariance matrix, the scaled identity, the identity matrix of length same as the random vector x. This is kind of a complicated version of what? Version of, let me use Z because this is more appealing. Because it's strongly related to the standardization of a random variable by using its mean and the standard deviation. Got it? So here, a second. Okay. So here, whatever mean and variance X has, Z is always zero mean unit variance random variable. Similarly, whatever mean vector and covariance matrix you have, as far as the covariance matrix is positive definite, not semi-definite, the square root, inverse square root exists, and you have what? The zero mean identity covariance matrix random vector Z. Be careful, I didn't say anything about the distribution PDF of Z. It could be Gaussian, it could not be Gaussian. Similarly, Z may be Gaussian if X is Gaussian, but in general, Z is not Gaussian. And also, even though we have uncorrelatedness between any two pair of Z, but it does not necessarily mean independence. Be careful. The uncorrelated implies independence if Gaussian. I'm not saying if and only if, but if they are jointly Gaussian. The next topic was related to the conditional mean and the conditional covariance matrix when you had Gaussianity. So in this case, we of Gaussian random vector. And what was worth to remember? The results was like this. Given the event capital Y equals Y, the conditional mean is the same as unconditional mean plus the correction term. And the correction term is, of course, a function of observation Y. Since the units of X and Y could be different, you have what? The first inverse of the covariance matrix. This is a kind of vectored as whitening filter, as you've seen already, right? You subtract, and if you represent this inverse covariance matrix as the product of two whitening filters, then you can group these terms to see what? To see exactly this one, right? You subtract the mean and multiply the whitening matrix. And then you here have the covariance between X and Y so that you have the proper unit of X. This is X to be added to the mean vector of X. Got it? And interestingly, when, of course, here X and Y are jointly Gaussian, okay? And interestingly, the covariance matrix given Y is not a function of Y. I emphasize that, and which is unconditional covariance minus, let me use the different notation so that we can easily remember. So we have CXX minus CXY, CYY inverse CYX. So this is very important when you have Gaussianity. And I also mentioned the importance of the characteristic function of a proper Gaussian, proper complex Gaussian random variables and vectors. In general, it's very complicated to have the characteristic function of improper complex Gaussian random vector, but in proper case, it's very simple. The third topic was mean square estimation, and surprisingly, the best affine approximation had the same form as this one. So it's like when X and Y are jointly distributed, your best approximate of X as a function of Y equals what? The mean of X plus covariance between x and y, the inverse of the covariance matrix of y, and y minus mu y. So you have the same form as this one. Got it? But I'm not saying that x and y are jointly Gaussian. Just x and y are jointly distributed. The best affine approximation has the same form as the conditional mean when x and y were Gaussian. And also, the covariance of the error equals what? Equals the covariance of x minus covariance of x and y and y inverse y and x. So you again have the same form. Very interesting. I'd better say not covariance, but the error covariance matrix. Okay, so this is kind of a performance measure of our affine estimator. By the way, if we stick to have linearity, not affineness, then we may have some different form. Okay, so be careful. A best affine approximation is not necessarily equal to best linear approximation. The final topic of the last meeting was the beginning of chapter 4. Section 7.4, stochastic convergence and limit theorems. In order to warm up, I gave you some preliminary analysis stuff. First, we started with the equality of two scalars, and then we learned how to mathematically say two scalars are approximately equal. The key idea is to construct a sequence of scalars that hopefully converges to the number. So here, suppose we want to claim x is very close to y. What we do is that we select x or y, one of them, and construct a sequence. And of course, this x is one of the x of n at very large n, for example, and then we show that the sequence xn has the limit y, something like that. Of course, sometimes we are satisfied just finding upper and lower bounds. For example, suppose we had no idea about the value of the pi, the circumference of a circle with diameter 1. Then the Greeks tried to use square polygons, regular polygons that inscribes and encloses, and then they increase the number of sides to have very tight upper and lower bounds, something like that. Anyway, so in order to talk about the limit and convergent sequence, we had to review the notion of a convergent sequence. Here, you must remember that original definition includes the limit. So you have to have the sequence and also a candidate of the limit, so that you could say this spec. For every epsilon positive, there exists n of epsilon such that for sufficiently large n, the difference between xn and x is less than or equal to epsilon. Whatever epsilon positive you choose, you must be able to find capital N of epsilon. If you, for some, there exists some epsilon where you cannot find such N of epsilon, then the sequence does not converge. So here is some correction. Last time I corrected the lecture note, but the handout had some I remember mistakes. So we must have this. The equality must be flipped here. Okay, something like that. This is one of the correction. And about the clarification, I'll talk about soon. And then in order to remove that requirement when using our definition, what is the requirement? We must have the candidate limit. Cauchy developed an interesting idea, which is very, very useful and powerful when we are only talking about the sequence of real numbers with some real limit. In that case, we don't need the limit to show that the sequence converges. So the definition is like this. Sequence xn is a Cauchy sequence when for every epsilon positive, there exists n of epsilon, of course an integer, such that if m and n are both greater than or equal to epsilon, then what? xm minus xn is less than or equal to epsilon. Okay, and here be careful. It's like suppose you have some so even though you don't have the target, it's like if you choose epsilon, some epsilon positive, and you find n of epsilon, then what happens? After that, whatever two number you choose, their difference is less than epsilon. Here, it does not involve the limit. However, you can easily find that if you are given if your limit exists, then so your sequence is convergent, then it's a Cauchy sequence. However, in general, the converse is not true. So what did I say? I said that if here is the set of all sequences, not necessarily sequences of real numbers, sequences in some domain, let's say, so sequence terms are in this D, then we have very small subset of convergent sequences. But if this is too small, we cannot draw any Venn diagram. So let me exaggerate. So here, convergent sequences. And then, it's too big, a little bit reduced. Okay. Then interestingly, there is a so-called Cauchy sequences. So this, here goes the set of Cauchy sequences that include the convergent sequences. So if the sequence is convergent, then it's a Cauchy sequence, but the converse is not true. Got it? But if that D is real, then they are the same. Anyway, this is different from very confusing thing. Consider some sequence x of n that is, let me see. No, just a second. Just a second. Yeah. So let's say the x of n is the summation of n terms, something like this. So x10 means you add 10 terms, right? And you know that this sequence does not converge, it diverges, okay? However, you can easily show that the adjacent two terms, if you subtract, then what do you have? It goes to 0. It seems the sequence is Cauchy, but actually it is not. Be careful. Cauchy sequence does not mean this thing. Cauchy sequence does not talk about two adjacent terms. It talks about any two terms after you cut at capital N of epsilon. So this sequence is not a Cauchy sequence, and it does not converge even in real domain. Okay. Anyway, that is the review and corrections and clarification. And today, we continue the preliminary kind of stuff related to the equality of two functions today. And hopefully, I want to move to the next topic of the equality of two random variables, but it's not likely. Anyway, so let's start from the equality of two functions. And what would be the difference between the equality of two scalars and the equality of two functions? In order to understand this question, we have to remind what is the definition of a function. What is the definition of a function? Suppose you have a function f. What does that mean? Actually, if you visualize, you have a mapping rule. However, a mapping rule has an admissible input that is called the set domain. And output is sometimes they use range, but we usually just use so-called codomain, but let me use R, okay? So we have domain and codomain that kind of talks about what is admissible and what is the rough output set, got it? This is not the exact output set. But anyway, and then we have usually mathematical formula to link between the input and output, but it is not necessary. What is another visualization method? It's like this. Suppose x and y are real numbers, then your graph is a very good way to understand. Be careful, graph is different from what? The function. See that? Function is a triplet. So you need domain and codomain and the mapping rule, right? And in order to fully specify a function, you need three things. So it's a triplet. What is a graph? Graph is not just a figure. Graph is the set of points. So it's a set of points x comma y, where x is in the domain and y equals the output. So actually, this is not the graph. This is the graph drawn, okay? So drawing a graph is different from a graph. Graph is mathematically defined, graph of a function, of course, not graph edge, note that thing. Graph of a function is defined the set of functions. And you visualize by drawing that. But anyway, so for example, this figure visualizes your graph. Then what does that mean? What does that mean by this figure that shows the graph? For each x, you have a pair number. So actually, you go back to the original definition, right? Got it? Now, given the definition of a function, or in engineering waveform, here goes the question. Suppose you have two functions, capital X and capital Y. So capital X has, let me just move to here. So suppose your function X has domain D1 and range real number. So we can handle real valued functions, okay? And function Y has domain D2 and the codomain, the real set. And to claim they are equal, let's assume that the something's wrong, domains, right? Domains are subsets of real numbers. Got it? So D1 and D2 are subsets of real numbers. In that case, these two are real valued functions of a real number, right? Now, what is the requirement to claim the function x is equal to y? By the way, we haven't yet defined the meaning of this, right? But we want to define it. So when do we say two functions are equal? And now, if you remember the definition of a function, which consists of three things, not only the mathematical rule, possibly using elementary functions, but also the domains must be the same, right? If you draw a graph, it's obvious, right? For example, your F1 and F2 graphs have some point in the domain that has different values. They are different. But that is not the only requirement. Their domains must be the same. For example, consider two functions, f1 of x, that is 1 over x for x positive. Consider x f2, that is 1 over x for x negative. Let me ask you a question. Are they the same functions? No, right? This is the this is what was very emphasized in the signal-gen systems too. For example, if two Laplace transforms have the same form, same rational function form, but if their ROC, reason of convergence, are different, they are different functions. Got it? So be careful. If domains are different, then they are different functions. Of course, you may say that on some subset of domain, they are equal functions. But anyway, so first thing is that domains must be the same. And second, at each point in the common domain, their function values must be the same. So how many equalities do we have to claim that two functions are the same? We need to show that the function values are the same for every input argument in the common domain. And if this common domain is an uncountable set, how many equalities do we need to check? Uncountably infinite. Okay? So suppose two real functions are the same given the interval 0, 1. How many scalar equalities do you need to check? Uncountably infinite. Got it? If you claim that two real-valued functions of real numbers are the same on the interval 0, 1, but for rational points, how many equalities, scalar equalities do you need to check? Countably infinite equalities. So now you suddenly realize that function equality requires much more than the simple two scalars equality. Got it? Now, here we define equal everywhere. So we claim and we write like this. See that? X equals Y everywhere. Or this notation, or somebody loves that. Very confusing. But anyway, they all read as X equals Y everywhere. Of course, everywhere on the common domain. Or everywhere on some specified common domain. Got it? Now, is it enough? Sometimes this definition is too strong. We don't need this. When? When we use functions to model electrical signals. We are electrical engineers, and we use the notion of time functions to model our electrical signals. For example, current, voltage, when they are time varying. But is it the precise and the unique and non-disputable model to handle current, voltage? Actually, we already now know that electrical current is carried by electrons in the conductor. And electrons are what? Discrete. They are quantized. Then every current, if you zoom in and in and in and in, it cannot be a continuous function, right? And also we know that since the position cannot be precisely determined according to the quantum physics, this time function to model electrical current does not make sense, right? Anyway, we already have some uncertainty. So we admit that the electrical current modeled as a time function is a simple approximation. So consider this. Suppose you have electrical current x1 and electrical current x2 modeled as two functions, and they are the same except at some specific point. Then are they really different functions? So it's like x1 of t equals x2 of t for all real number except t0. So t0, t0. Then we just say that, oh, I am sorry, two functions are different. It does not make sense because usually in electrical engineering, what is important is energy. We want to transfer energy from here to there so that at destination, something happens, like the information stored in memory is changed, right? Or some information is given. Everything is conveyed by energy. And if you just change at one point, then the energy of any small but positive, non-negative interval does not change. Even, for example, at this point, around this point, as far as you have a positive delta, then energy inside this interval is same as energy inside this interval. And you may say that at almost every point, they are the same if you reduce delta, right? Then you now realize everywhere equality is too strong for engineering application. Then what do we do? So here goes a relaxed version of equality of two functions. Now what we do is that we calculate so-called measure of the set where two functions are different. So you see that in the domain, common domain, we find the set, subset of the domain called common domain, where two functions are different. That is the first step. And second, we measure the size of that set where two functions are different. If the size is 0, then we are happy. And you may say that how can we measure the size? That depends on the various definition. But one of the idea is to use the Lebesgue measure of the set. And what is the Lebesgue measure? Simply put, if you have countably infinite set, the size is 0. Just remember, which means that the set of all rational numbers, even though it includes countably infinite numbers, the size is 0. What does that mean? The most important and memorizable example is this one. Suppose you have a function x1 that is the indicator function 0, 1 intersection q of x. What does that mean? So function has value 0 for all irrational numbers on this interval. And of course, outside the interval, they are zeros. And if they are rational, then it's 1. right? Now, this function and the other function is to be compared. Now, let me ask you, what is the set of x such that x1 and x2 are different? Of course, this is the set of what? Set of rational numbers on this interval 0, 1. And as I just told you, what is the size of this set? 0, which means that they are, in some sense, equal. They are equal for irrational value of x and all values of x outside this interval, right? So in this case, we call these two functions are equal almost everywhere. Got it? This goes the abbreviation A dot E dot, almost everywhere. So x equals y everywhere is too strong, and x equals y almost everywhere is a relaxed version. Now let me ask you a question. X equals y everywhere implies almost everywhere? Yes, of course, right? Because this set is the empty set. And the empty set has no entry, so measure is 0. Got it? But if the different set consists of finite number of real numbers, countably infinite number of real numbers, it's okay, because we usually handle the codomain, the uncountable set. And if we subtract out, if we take out some finite or countable points, it's okay. Got it? And now, here goes some let me see, just a second. Yeah, here goes some interesting thing you need to remember. So here, you see, we considered what? How many equality, how many scalar equality does this definition involve? First, at the outermost shell, we have, this is a scalar, real scalar equals 0. So we handle single equality of the measure of the set equals 0. But to define or find this set to be measured, how many points do we need to check? Again, uncountably infinite scalar equalities. But anyway, by introducing the set, we kind of use the scalar equality. This is a very important trick when you have difficulty in representing your idea. For example, yesterday, I spent a lot of time to very concisely but mathematically simply to describe some idea to deliver for my project. It took me hours, actually. But the last resort was to introduce so-called index sets. And I said that this index set is a partition of the universal set, which means that union of these things becomes the universal set, and what? The intersections are empty sets, something like that. And then also I added like, okay, each index set consists of at least one number, and if there are more than 2, then the numbers must be consecutive, something like that. Okay, so introducing the set is very, very important. So here, the idea is that they introduce the set where on which the two functions are different, and then they measured the size of this set to define the almost everywhere equality of two functions. And this definition can be rewritten in that form. And now see the difference. See that here we used that for every epsilon positive that spell, magic spell, right? We love that. So here, for every epsilon positive, now for each epsilon, you find the set that is parameterized by epsilon. Now you allow the difference less than epsilon. On the other hand, you do not allow the difference larger than epsilon. So instead of allowing no difference, see that this is no different, right? You little bit give the freedom. This is the idea, main idea of every analysis. When you introduce the sequence, this is what you do. So you have a little bit room to maneuver. Anyway, so for every epsilon positive, probably very small, right? And then you compute this one. Of course, if x of s, y of s are their difference are bigger than some positive epsilon, of course they are different, right? And this set, if this set is measured and 0, well, then you are happy. You say that, okay, function values, two function values are less than epsilon everywhere. But here we have another thing for every epsilon positive. And then actually you can easily see that this is the same definition as that one. And at this point, this is not that important. You may say that, oh, this is a trick. Yeah, you are right. However, we are going to see this form when we talk about sequence of functions. That's why I'm talking about it. And another thing is this one. Consider this integration. Suppose P is a real number greater than or equal to 1. That is very important. If it is less than 1, you have nothing. Okay, you have very big trouble. Anyway, greater than. Now, you subtract and take the absolute value if they are complex valued modulus, and then raise to the power of P, which is greater than or equal to 1. And then you integrate this error function, error raised to the power of P on the common domain. And if this is 0, what does that mean? You can easily show that what? They are equal almost everywhere. So in the engineering sense, this makes sense when P equals 2, right? Why? Because if P equals 2, that is the energy of the difference signal. And if the energy of difference signal is 0, what does that mean? Nothing happens at the other side of the electrical system. No energy transferred mathematically, right? So this is very good. Okay. And here, they are the same when you talk about only two functions. Got it? So it's like we are very, very happy. We now have introduced the notion of almost everywhere equal functions. And it seems that this definition is enough for electrical engineers. And I'm sure you are correct. The problem is that, the next topic, what if we want to claim that two functions are almost equal? Then we have to construct what? A sequence of functions. And you want to claim that for sufficiently large n, right? X of n function is almost the same as y of s function. Got it? So as I did last time, we started from the equality of two scalars, and that was okay. And then we considered two scalars approximate equality. And one way was to introduce the sequence of scalars. Now we move our topic to two functions. And for equality, we just didn't say they are equal everywhere because that was too strong for engineers. So we developed the idea of almost everywhere equality, and we were happy. However, in order to talk about, as we did for the two scalars, to talk about approximate equality of two functions, if we follow the same idea, we need to construct a sequence of functions. Now, we want to define the convergence of a sequence of functions to the target or the limit function. Then, what kind of definition do we need to develop? When we talked about sequence of real numbers, that definition, for every epsilon positive, there exists n of epsilon, blah, 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 was okay. And now, does that enough? Is that enough? And the answer is, of course, no. That's why we talk about this topic. So let's remind your friendly Fourier series. What was the Fourier series? For example, in the continuous time, given a periodic signal with period some capital T, which is positive real, what do? We approximate the function. We approximate the function x by using its, let me see, so-called Fourier series representation. So here, I start not to like this. Okay. Let me use tilde here. So there are two functions first. First thing is x of n, which is, I love right continuous function. So let me draw this way. Got it? You know what I mean, right? So here we have discontinuities at every half t. This is period capital T. Got it? This is it. So x of t is a periodic signal, periodic square wave that is right continuous. Now, given this function, what did you do in signals and systems? You derive Fourier series coefficients. And you derive the Fourier series coefficients to rewrite x of t using what? Using a series of function. So here goes x tilde. Be careful, I didn't say this is x. Now x tilde is defined as the sum of your Fourier coefficient times sine function. In this case, the cosine terms are all zero because the function is an odd function. Okay. So you have sine 2 pi kt over capital T, where k runs for every integer. And sometimes you truncated this infinite sum to a finite term. For example, sorry, something's wrong. Sorry, not every k, every integer, every natural number in this case, because the a0 is 0 because mean is 0, and you only have positive terms, right? So a sub 1, a sub 2, blah, blah, blah. So x of n is the truncated version of Fourier series. Now, what about this one? This is a finite sum of weighted sinusoidal function. So it's well defined. And whenever you have finite terms or continuous, the sum is continuous, right? Sum of continuous functions is continuous when you add finite terms, right? So these are continuous functions. Now you increase this n, million, trillion. What happens? Still you have a continuous function. You never have this discontinuity. And even if you consider x0, xn of 0, and take the limit, then what happens? In this representation, you always have 0. What does that mean? If you define this one as the limit of right-hand side at each point t, what is x tilde of 0? That is 0, which means that x tilde 0 never becomes 1, for example. Neither negative 1. Now, what about this sequence of functions you construct by changing this subscript n? So you have a function x1 of t, function x2 of t, function x3 of t. Now, can you claim that this sequence of functions converge to the original sequence? And if you remember the equality, you may want to check the equality of two functions xt and x tilde t by defining the value of this function as a pointwise limit of the right-hand side, which means that you consider the limit of this sequence xn at each point, right? And of course, you already know that they are not the same. Then we just say that, okay, x tilde equals x almost everywhere. That is actually one of the correct idea to talk about the convergence of a sequence of functions. So what you do is this one. You construct a sequence of functions in this case. So x1, x2, x3, okay? And you have this notation. The sequence converges to x of t almost everywhere if what? Limit xn of t when n tends to infinity equals x of t, right? So you find this set for all t in the domain, right? And the size is 0, then you may say that they are almost everywhere equal. Am I right? And then this motivates us much stronger definition. Okay, then we may say that this converges to x of t everywhere. If what? If this set is empty set, right? See that? This is where the limit of the functions is different point-wise to the function. And if this is an empty set, so they are not different, then everywhere converges everywhere. In this case, the set may be non-empty set, but its size is 0. Got it? When it is measured by a metric of the set, it is 0, then we say almost everywhere equal. Got it? So this very famous Fourier series of the square wave of right continuous square wave is what? A good example of almost everywhere convergence. Got it? They are not the function, the sequence of Fourier series approximation does not converge everywhere. As you say that at every discontinuous point, the sequence does not converge. The sequence defined as the truncated series of Fourier series. Got it? It's very complicated, but anyway. So we've just seen everywhere convergence. That means at every point of time, right? In this case, if it is a time function. So this is called point-wise convergence. And this is called point-wise everywhere, almost everywhere convergence. But its point-wise is too cumbersome. So just say that converges everywhere, converges almost everywhere. And our notation is almost the same. So it's like limit n tends to infinity, capital X sub n of s equals y of s everywhere. What does that mean? Yeah, they are everywhere. The sequence of functions xn converges y of s everywhere. And also, we have the notation limit n tends to infinity, x sub n of s equals y of s a dot e dot almost everywhere. Got it? So they are different definitions. And let me use different color so that we can easily distinguish. Ready? So we have two definitions, but the problem is this one. Sometimes in engineering problem, what we want is that if we just stop at some point, so we have a sequence of functions and we choose sufficiently large n, and what we want is that the two functions are bounded by common epsilon. So it's like, see that? Your function, the nth function xn, and some limit function, your target function x, if their difference is bounded by epsilon for all s in the domain, which means that, what does that mean? Their difference is bounded by epsilon. So if you rewrite this one, how can you say that? Xn of s, x of s is xn of s plus epsilon, xn of s minus epsilon, right? They are the same, right? As you learned in middle school math. So what can you say is that you don't know the true value of x, but you know the approximation. And you are guaranteed to what? If you draw upper and lower bounds, plus epsilon minus epsilon, then your function x is definitely inside that gap. You want sometimes that definition of convergence. But as you learned in signal-gen systems, simple Fourier series gives you so-called the Gibbs phenomena. That is the phenomenon discovered by Gibbs, not Gibb, okay? Gibbs is the last name. So Gibbs showed what? This famous function and its sequence gives you strange behavior. For example, if you choose very large value n, but still you have what? You have even though for all continuous points or continuity points, you are guaranteed to converge, but around the discontinuous points, whatever large n you have, your error does not decrease. So you cannot find epsilon on which you say that, okay, my function is there. You can't say that for this one. But then maybe very critical in some applications. So people devise the idea of uniform convergence. What does that mean? The definition is very similar to the notion of sequence of scalars converges to scalars. See that? For every epsilon positive, there is the n of epsilon. So far, everything's the same, such that if n is greater than or equal to epsilon, so far the same. Now see the difference. This implies the error is bounded. And what is the key? This one. For every value of s in the domain. Got it? So using a single margin epsilon, you can bound the function. If that holds, you can find such n of epsilon for every epsilon, then you claim that function converges uniform. And an example is like this. This is very strange, but an example is like this. For example, you remember this series of e to the x, right? You remember this one from your math. First question, are they equal at every point of x real? Can you claim this? So which means that the right-hand side at each point of x converges to e to the x, which means that my question is that right-hand side as a sequence, if you truncate up to some k, does it converge to the left-hand side point-wise? Yes. Okay. So the sequence, let me say fn of x defined as not n, m, let me use sigma n from 0 to m. Okay, so fm of x converges to e to the x everywhere. This is the answer. Okay. Second question is that, does this sequence of functions converges to e to the x almost everywhere? Of course, everywhere convergence implies almost everywhere convergence. So almost everywhere convergence. Third question, does this sequence of functions uniformly converges to e to the x? The answer is yes. Okay. This is a very good example. It uniformly converges. However, whenever you have discontinuity, the periodic function, discontinuous periodic function gives you what? Gives phenomena. So Fourier series never gives you uniform convergence if the interval includes point of discontinuity. Got it? So we have introduced 3 definitions. The first one is uniform convergence. And it seems it's very, very strong because see that using a single epsilon, you could bound xn and the limit for every x in the domain or every s in the domain in this case. Now, does that imply everywhere convergence? Of course, yes, because everywhere convergence required at each t, or in this case, s in the domain. You required some epsilon sub s and n, capital N of epsilon sub s. But now in the uniform convergence case, you could do that using a single epsilon. But so it's much stronger definition. So uniform convergence implies everywhere convergence. And everywhere convergence implies almost everywhere convergence. So we have 3 definitions. So uniform convergence, everywhere convergence, and almost everywhere convergence. Got it? So far, so good. Okay. But as I told you, as an electrical engineer, do we really need uniform convergence, everywhere convergence, or almost everywhere convergence? No, actually. As I told you, energy is one of the most important things, right? So we want to talk about something like this. So here goes the difference. We have what? The target or the limit function, x. And we have a sequence of functions. Let me not use x and y. Let me use x sub n and x. Got it? Now, you take the difference and compute, for example, the squared error when p equals 2. And then you compute the energy on the domain, common domain. Now, this energy may not be 0 in general. However, if you can show that the left-hand side, by the way, what is the left-hand side? A sequence of real numbers, right? The nth term of the sequence of real number. If that converges to 0, so energy parameter, energy of the difference, error energy, when p equals 2, parameterized by n, converges to 0, which means that if you take for sufficiently large n, the energy of the error signal is sufficiently small. Then you may say that, okay, in terms of energy, no change. The signal is what? The same. Got it? And this definition is what? Called the convergence of the sequence of functions to the limit in the p's mean if p is a real number greater than or equal to 1. So how many definitions do we have here? Actually, you have, again, uncountably infinite. So even though I just say that we have fourth definition, this fourth definition has what? Uncountably infinite definitions, because p can be chosen from 1 to any real number, right? So the most popular choice is 2, but it's not necessary. Got it? Anyway, when we have p equals 2, we have a good notation. And as a graduate student, you must remember this one. Because when I first saw it, I thought that there is a typo. See that? L dot I dot M dot? Probably typo. We just use lim. No. What does that mean? This is what? Limit in the mean. That's why you have LIM. Got it? Limit in the mean means that the sequence xn converges to the function x in the mean square sense or in the second mean. So we just use this definition with p equals 2. Got it? So mean square convergence may be a good choice for engineers when we are concerned with the energy that could change something at the other side of the circuit. Got it? Now, one interesting thing is this one. Now let me draw it here. So uniform convergence is the strongest. And this implies everywhere convergence. And this implies almost everywhere convergence. What about the relation between the convergence in the pith mean and the convergence of these sense? Amazingly, they are not related. So you have different branch convergence in the pith mean with p greater than or equal to 1. You can find an example where you have convergence in the second mean. So you have a limit in the mean that does not even everywhere convergence. Almost everywhere convergence. Got it? And here I want to say that, see, you remember this one. Right? You remember this. When we considered only two functions are equal on the common domain was the same statement as this one, right? However, if you consider sequence, they are different. They are not related at all. They do not imply each other. Got it? This confuses a lot. And here was something more confusing. By the way, we have convergence in the pith mean in terms of Cauchy sense. So a sequence is a Cauchy sequence in the pith mean, sequence of functions. when we have this. Got it? So in the second mean, in this case, in the second mean, the difference and raised to the power of 2 and integrated if this sequence goes to 0. So you remember xn is Cauchy if this is definition, if what? For every epsilon positive, there is n of epsilon such that n greater than or equal to n of epsilon implies mn minus xn less than or equal to epsilon, right? Now, if I write down side by side x sub n of s, n is a Cauchy sequence of functions, right? Here, upper side is Cauchy sequence. The lower side is Cauchy sequence of functions if for every epsilon positive, there is the n of epsilon, a natural number such that mn greater than or equal to n of epsilon implies xm of s minus xn of s squared and integrated is less than or equal to epsilon, right? Less than or equal to epsilon. Got it? Cauchy in the second mean. If you replace this 2 with p greater than or equal to 1, then it can be generalized, okay? And this definition is, again, not related to what? Anything on the left-hand side. You also remember something similar to this one. What was that? For every epsilon positive, I introduced some set, right? And said that this equals 0 if and only if x equals y almost everywhere, right? So now what about something similar to this one? When we have a sequence of functions. Again, this gives us a new and different definition. And that is this one. Convergence in measure. And see that? As you see, we start with, for every epsilon positive, the measure now, because we have a sequence, tends to 0. So this definition involves what? Sequence of real numbers that is computed by measuring the set on which the limit function and the nth term has difference greater than epsilon. So if you have a bound, then from x of n with plus minus epsilon, x of n may deviate from the bound, and then you take down all the values and construct the set for each n and epsilon. And then you construct the sequence of real numbers by measuring that set, parameterized by n and epsilon. And if that sequence converges to 0, then your convergence of the function to another function in the measure sense. This is convergence in measure. And interestingly, we have a good implication. Convergence in measure. And also, this right branch of convergence in the pith mean implies this one. So they are kind of converges to the same thing. And these 1, 2, 3, 4, and actually infinite, but let's say 5 definitions are very important in the mathematical analysis. And you may say that, wait a minute, it seems very similar to what I was taught in my undergraduate probability and random processes course, where professor talked about 4 convergence modes for the sequence of random variables. Actually, only this one, that one, and that one, and Let me see. Sorry, not this. And there is another one. These four things are useful when you talk about probabilities. And you already know that what is a random variable? Random variable is a function. So it seems that we have these 5 definitions, right? I just introduced, applicable to a sequence of random variables. However, we don't need these 2. They are not useful. So these 3 are useful, and we have one more that is called convergence in distribution. Of course, convergence in probability distribution. And we talk about what? As you learned in central limit theorem, we talk about what? Characteristic function or cumulative distribution function. Anyway, so I very quickly reviewed the sequence of functions part, and actually I'm happy to finish this part. Next time, we are going to move to what? Equality of 2 random variables first. And then we are going to talk about how can we approximate a random variable using another random variable. Again, we introduce a sequence of random variables and talk about the convergence of a sequence to the limit random variable. Okay, that's all for today.